Hello and welcome to our webinar about test fixture de-embedding for high-speed digital applications. We will talk today particularly about fixtures that are being used with oscilloscopes, and we will have a special focus on the fact that these fixtures do not necessarily have a 2x through, but they still, in many cases, need to be characterized and de-embedded. My name is Martin Stumpf, Segment Manager for High-Speed Digital Design in Rohde & Schwarz. And I'm joined today by my colleague, Matthias Hellwig, Application Development in Rohde & Schwarz. We also have a colleague from Würth Electronics who has helped us here with this webinar. His name is Fabian Altenbrunn. He will join us later. Let's get started. So this picture shows already the fixtures that we are going to talk about. A fixture with a receptacle and a fixture with a plug. And you already see the challenge here. These fixtures do not have a 2x through. So how do we characterize them and how do we de-embed them? Before we go into the details, maybe a quick recap in terms of test fixture modeling and de-embedding. This slide here shows the structure that we have. We have a device under test. This device under test does not have a coaxial connector. It requires a lead-in and a test fixture to adapt the non-coaxial connector to a coaxial connector. This is what we see here on this side. How do we characterize? We need a reference structure. This reference structure typically is a 2x through. The 2x through consists out of a replica of the test fixture model and a mirrored replica of this test fixture model. What do we get out of this? We get the model for the lead-in. This is what we are using here. And of course, with this, we can characterize the DUT by itself, which means we are shifting the reference plane directly to the DUT. How is it implemented? Typically, this test fixture characterization is being done with network analyzers. How is it implemented in the Rohde & Schwarz network analyzers? You see here we have 3 different options. In this webinar, we are going to use the option K220 ISD. You also see the different de-embedding coupons that can be used. A 2x through, 1x open, 1x short as a combination, and 1x open and 1x short separately. At the bottom, you see the de-embedding assistant implemented in our vector network analyzers. This de-embedding assistant guides you through the definition of the topology, the measurement of the coupons, and the measurement of the total structure. In this webinar, we are particularly talking about these fixtures. On the one hand, the fixture with a plug. You see that on the left side. On the other hand, the fixture with a receptacle. You see that on the right hand. Both are USB test fixtures. We use them as an example because USB test fixtures are widely used, very widely available. And as you can see, they do not have a 2x through. They also typically do not come with S parameters, but in case we want to de-embed them, we need a method how to do that. The method basically is build your own reference structure, build your own 1x open, your own 1x short. And with this, you also do not only move the reference plane away from the coaxial connectors close to the USB connector, you move the reference plane even into the USB connector itself. And of course, this is an example for a USB, but it equally can be applied to other technologies like DisplayPort, like HDMI, like PCIe and others. With this and a big thank you to Würth Electronic, I would like to hand over to Fabian. Fabian has helped us providing a 1x short for this webinar preparation. And with this, I would like to hand over to Fabian.
Thanks, Martin. First, I would like to explain the function and with a side view, what is the main function of the receptacle and what is the main function in contacting of a plug. On the left-hand side, upper, you see the receptacle with the contacts of the middle tongue. And on the right side, you see the plug with 2 spring clamps beside of it. In the middle side, when you see this side view, you can see how the plug contacts to the receptacle. The plug normally contacts to the receptacle by the spring clamps, and when you only insert a cable connector or the shortcut device, then you need an additional function. And you see it on the side view in the bottom. There's also on the receptacle housing a small spring clamp who ensures that the right forces are between the contacts of the shortcut circuit device on the plug and the receptacle. On this slide, you see what is the main function and why we would like to offer to you a shortcut circuit device. It's better to have a track termination. That means that you can insert this shortcut circuit adapter to a plug or receptacle and you have a defined end position. So you can measure all lines by themselves. With these simulation results, without any peripheral devices, cables and so on, you have only the product itself tested. The measurement can also extend it not only to data transfer, you can also test the derating function during the power delivery mode. So this is important for us as component manufacturer, so we can test each component by themselves when we have the inrush current, how is the derating curves and what is the maximum amps and current, the maximum amps and voltage we bring to this connector, and what is the heating curves. After the results and the co-workshop with Rode and Schwarz, we can bring these measurement results to customer and you can use it for validation of your PCB design. We can use it for our connector design. And with these parameters, you can prevent circuit layout routing errors. For example, when you have on the configuration channel some missed configuration, you missed a capacitor or so on. And also when you have a misrouting between D1 plus and negative and also D2 plus and negative. And this is important to ensure that the first prototypes are really working well and not tested by product themselves. On the right hand side, you see the dimension and you see the surface and the shape of this connector. It's really small and you can use it for both types. So you have only one short circuit adapter for both types, for the receptacle and for the plug version. And on the last slide, you can see how it looks like in real. On the left side, you see the plug version with the short side of the short circuit adapter. And on the right hand side, you see like the U form that you can insert in the receptacle mount. And you see also the springs at the housing edge who ensures that you have every time the right contact and you have a good electrical dimension to all of them. So thanks for to being here. And now I would like to get over to Martin.
Thank you, Fabian, for the introduction of this 1X short. With this, I would like to hand over to my colleague Matthias. He will give us an update about how the measurements are done, what the challenges are, and particularly also compare a couple of different measurement methods in terms of the Deembedding. Matthias.
Yeah, thank you, Martin. Going to the measurements, it's split in two sections. The first section takes care of the VNA measurements. And for the VNA measurements, we like to refer to the consistency checks as are defined in the IEEE 370, the standard for characterization of PCB and related interconnects. There are multiple suggestions how to test the test fixture and do a qualification of that. I labeled that with test 1, 2, 3, 4. The first two are normative, and the second, the third, and the fourth are informative. Particular focus here on test number 2, which is sort of the fixture DOT fixture test with a TDR. But I also like to point out that these tests are relevant, but not well suited for single-side fixtures. Problem here is you sometimes don't have a 2x through, as Martin explained, so I'd like to add a consistency check number 5, where I do a de-embedding the model on the open and the short, which we measured so far. The deviation in the TDR from the reference impedance is the quality measure of the fixture, and this just works for one side, which might be helpful for you. Let's have a closer look on the VNA measurement setup. We typically do 4 measurements, or 4 measurements are possible for a single side fixture model. There is the coupon 1x open, which I will call open in the next future. The coupon 1x short, which I will call short. The total structure fixture, left and right, I would call that 2x through. And the total structure, the fixture left and the DOT, I will call just DOT. For the model generation, we need 2 or 3 VNA measurements. 4 configurations can be generated. I will walk through that in the next slide. And before we go to the overview, I will quickly pick up something which is called a bisection of the fixture. This is very popular. A lot of people do that. And this is sort of a workaround if you don't want to measure that individually. And I want to show you the effects of that. We have a symmetrical split, a bisection of 2 identical coupons, just in the middle. And mathematically, it's defined with an S-parameter matrix SC that is measured. And that should satisfy squared together the measured S-parameter matrix. There are tools in MATLAB and Python that can do this. But the issue is, typical data connectors are not symmetrical. The split is mathematically correct, but the fixture does not match the real fixture. And so for the analysis, this model is carried on, labeled with symmetrical 2x through. So here's the overview, what we're doing. We have a configuration and we have a label of coupon and structure, and we have measurements. You see the measurements 1, 2, 3, 4 with open, short, 2 times through, and DOT. And we have pros and cons. And what I can tell you up front is that symmetrical 2x through configuration gives you a wrong model. It's a simple setup. Only 1 measurement is required, but it will not give you a good result. The next is the open 2x through, which requires an open measurement and 2x through. There's no short required. It has a little bit lower accuracy, but it requires 2 fixtures, left and right. And then as an addition is the open short 2x through. Similar to the previous one, it has a higher accuracy. It allows model generation for left and right side, and you don't need something specifically on the startup pattern. Con on this side is essentially that you require a short. You may not have always a short. And similar to the next part is we now abandon the 2x through. We go to the open DOT, use the DOT, an open measurement and the DOT. No short is required, and this allows the model generation with just the fixture, with 1 fixture. A little bit lower in accuracy, might require a special startup for the receive side if you look into that. Last, we have the open short DOT. Again, here a high accuracy, model generation with 1 fixture. Here you have to keep in mind that the DOT typically sends out data on the transmit side, and it also can require a special pattern for the receive side. And it requires a short. What are setup constraints? I like to introduce you a little bit into that because it's not always straightforward to do that. As we already talked about, certain setups require a 2x through, which might not be possible. This is not applicable for USB, but other standards may have an issue creating the 2x through. You can circumvent that with 2 return loss measurements. One is the open fixture, and the other is the fixture connected with a DOT using the VNA and measuring single-sided. The second constraint is typically a DOT with a high-speed digital interface has a dynamic termination typically and must be powered in order to apply the nominal termination impedance. If you don't apply power, you either have 0 or infinite impedance, and that is fine, you can power it, but keep in mind the transmit side typically sends out a data pattern, which is the CP0 pattern. We'll come to the implication later on what that means. The termination may only be applied after a specific link initialization. Using the USB 3.2 as an example, there is on the receive side a state called RX detect. So the impedance is not matching initially, and it expects this specific sequence, which is a common mode pulse, before it applies termination. And I added the state in the standard where you can find this. And this might be difficult to implement that with a VNA. Keep that in mind. VNA analysis models, what we did, so we did the 4 measurements, we generated all the models the 5 models that we have. And we compared this with the 2x through. The 2x through is the trace number 10 in blue going through. And so this part here. And what you can see is this is essentially very similar to the consistencies check number 2. And we have the 4 models that we are comparing. And most of the models work pretty well. You see with M1, the marker M1, at the location of the TDR of 472 picoseconds. That is the point where the device fixture is sort of at the end. And that works for most of the models except the 2x through. You can see already it's a symmetrical split, and it's somewhere in the middle. It's around 1.2 nanoseconds, so it's way above the previous measurement with the marker M1, and that indicates already that this is probably not the correct model that we're looking for. Going forward, we now analyze the VNA model, the models created with the VNA. We use the TDR analysis of the open and short and de-embed that with a model. This would be what I labeled before, the consistency check number 5. Here we have 4 diagrams. The top row indicates that we use the 2x through. The bottom row indicates that we use the DUT. The left column is the model generated with an open and a short, and the right column are the models generated only with an open, not a short. The de-embedded traces were shifted around the electrical length of 472 picoseconds because de-embedding means you shift the reference plane. And what you can see now is that you have a good coincidence of the open and the short. So the trace here is pretty stable until the open point when the fixture ended, and it is then consistent with the output. You can check the limit lines that are added. So we can show that all the models have an impedance accuracy of 7.75 ohms plus minus, and that means we have created a nice model that matches very well. The TDR of the 2x through measurements is not shown, it's not required, but it's shown here just for reference so that you can find your way to the consistency check number 2. Model properties. Now we have our models, we tested the models, we see that they look great. Have a deeper look into the models. The properties of the models here, which are compared, is phase, magnitude, and delay. So again, same scheme. The top row is the 2x through models. The bottom row is the DUT model, or other DUT models. The column with a short is on the left side. The columns without a short is on the right side. What are our findings here? Phase and delay deviation, I have to add, is the phase and delay from the linear phase delay. That means we subtract that. You see that by this offset marking in the VNA. Going forward, we see that the models generated with a short show a little bit of noisy behavior, most obvious in the delay measurement or the delay analysis, but also in the phase. And we'll have a closer look into that. The models generated with without the short show a ringing at the higher frequencies in magnitude, which is also not exactly what we expect here. We're using delta markers to analyze the ringing. On the green curve means the delay. We measure a periodicity of 129 megahertz. And on the phase curve, the red curve, we measure a periodicity of 2.4 gigahertz. We come to that later. We do a quick check. We're selecting the model created with an open short and a DUT. And this looks quite noisy. As I said before, we have noise particularly in the phase and the delay, a little bit less in the magnitude. And you can see here the MEM traces, MEM4, MEM5, MEM6. What I did now on the VNA, I applied a time gating. I used this information from the offset, which is 472 picoseconds, so that my time gate from -1 to +1 nanosecond, and applied that, and you see the corresponding traces. You see that all the ringing is gone, the fine ringing on all the traces. you see that there's a deviation at 0 hertz and at 20 gigahertz roughly. That means the model is not very accurate with the gating, but it shows the trend that the conclusion is the model is non-causal. Let's have a look why that is. We do a model adjustment. Why can the model not be causal? There are a few reasons. The first reason is definitely some mechanical reasons like cable flexure, residual errors after calibration. But also very important is you're measuring here into this active device. I used the transmit 1, and the device is sending out the CP0 pattern, and that interferes with the VNA measurement. Then you have also cable drift and minor things with connector repeatability and calibration drift. We selected now again this open short DUT model, and we are comparing now this model. First the original, the uncorrected model. Then we created a model where we have a simplified TDR gating in the time domain. We also used a complete causal model. The message is not discussed here. It would take us far off where we are, using the Kramer-Kroenig relation as a causality check. And we use the model without the short, so just the open DUT model. So we just looked here at the phase of the models. We have 2 traces that show ringing again, which is the uncorrected model, and the TDR-gated model, trace 4 and 5, shows us ringing. The causality-corrected model, trace 10, shows the lowest deviation and is without ringing. And the open DUT model, trace 16, is smooth but deviates much more. Going forward, we will look at the magnitude, and just in addition here, the ringing with 1 degree plus minus is already quite excellent value for the instrument and for the model here. Keep in mind, this is not the measurement, this is the model as we talk about. Going forward, we also look at the magnitude. So the first is the trace 1 shows again the ringing of the uncorrected model. The trace 2 looks fine and is coincident with trace 9. Trace 2 was the TDR-gated model. Trace 9 is the causality-corrected model. That looks also perfect. The open DUT model shows an issue at higher frequencies, starting around 12 gigahertz. There is sort of like something like a ringing. And at lower frequencies, let's say between 2 and 4 gigahertz, it deviates from the linear slope pretty much. So let's have a look at the practical VNA measurement. We set up a 2x screw, and we'll look at the VNA for return and insertion loss, and we'll analyze it in detail there. So we see that the VNA is calibrated, and we have just a single port on display. We start the sweep here, and now we go and change the balance port to 2 times balance port. As we have a differential structure, we add the trace. We change the trace measurement to the insertion loss. We set the marker, and now essentially we wait for the results to be displayed. We see insertion loss and return loss. We shift the marker to the equilibrium of both, and we see it's around 8.5 gigahertz. Now we're going to the Deembedding assistant. We see that we have the Deembedding assistant. We don't use the same coupon left and right. We want to measure here the 2 times through. We configure that. We see we have a 20 gigahertz bandwidth, which is important. And here we can configure the coupon A and B. I already recorded the measurements here, and I can load them quickly. Once I loaded the coupon A and B, I can run the measurement. And this will do the measurement. Once that is captured, we basically can press apply, and then the software on the VNA will generate our model. Once the model is generated, we see now the automatically de-embedded model together with the measured 2x through for return loss and insertion loss. That's displayed here. So that is the process of generating the model. Now we can turn back to the VNA analysis summary that we did. So here summarizing all the details that we found. We generated 4 models of the left side test fixture generated for the transmission part. We found no large difference between the model generated either with a DUT or a 2x through. The model with a short looks a little bit more noisy in delay, phase, and magnitude caused by non-causalities. The magnitude for the short models means they're using a short, don't show ringing within high frequencies. The 2.4 GHz marker, which I referred earlier to, corresponds to a length of roughly 30 millimeters. That is the length of the test fixture and is caused by multiple reflections inside the test fixture. 129 megahertz marker corresponds to a length of about 700 millimeters. That is roughly the length of the coaxial cable of the VNA. A causality corrected model based on an open short DUT model show no ringing and the expected behavior. The TDR gating here, by the way, is insufficient. Overall better behavior in magnitude, delay, and phase compared to the models without the short. And only this model has the benefit of the short measurement. Having said that, we're going to the next part. As I explained before, we split it in 2 parts. One is the VNA measurement. Now we're going to an oscilloscope measurement. And here we want to understand what is the implication of these models on the oscilloscope, what is important here. But in order to look in the details, let's have a look what we are looking for. We use an RTP 164B with the advanced jitter option and the advanced eye option. And we're doing an eye pattern measurement and then an advanced jitter analysis. Both we do for 5 as well as 10 gigabit USB signals. We set the horizontal time base to 40 gigasamples with an acquisition time of 200 microseconds. And we use channel 1 and 3 in a differential mode with channel 3 deskewed. And we have a special trigger, which we call the CDR trigger. The relative bandwidth set to 500 or 667 with respect to 5 and 10 gigabits per second. This is according to the standard. And for the deembedding, here one important remark, we'll see that later on in the hands-on. It's important to model all the components even if their insertion loss is low. Phase needs to be correctly modeled. People sometimes forget to use cables, think it's not important, but cables shift the phase, so that is important. Do not forget that. The oscilloscope setup that you can see in front of me consists out of an RTP, where we capture channel 1 and 3 on the transmit side. We have the test fixture 1, which is that one that we analyzed with the VNA, and we have models for that. We use the ARP generator inside the RTP that is connected to receive line 1. While we're doing that, the ARP asserts an LFPS pulse to change the compliance pattern, and this requires a second test fixture to convert the coaxial part to a standard USB cable here. We start with the CP0 for the 5 gigabit mode, and we have CP9 or CP12 for the 10 gigabit mode. And we have an NGP 804 for the DUT power supply that delivers 5 volts and 1 amps as standard for USB. After explaining the setup, let's have a look at the eye pattern analysis. As we said before, we're using the advanced eye tool with different fixture models. The measurements we do are rise and fall time, 20-80%, was measured on the waveform. We measure the eye height, width, Q factor, bit rate, and jitter on the eye, and the total jitter on the waveform histogram. The top right screenshot, we see the eye pattern with no deembedding. The bottom screenshot, we see the deembedding of the symmetrical 2x through. And notice already the strong de-emphasis that there is an overshoot as well as in the pre-shoot here. This is specifically for the symmetrical 2x through. Going forward, we see here the top right-hand screenshot, the model open short DUT embedded. And here we see that the eye here is more open than without the deembedding, but you don't see any kind of overshoot. So the summary is comparing the models that we had. We have no deembedding, we have this, and then the 5 others with symmetrical, open 2x through, open short 2x through, open DUT, and open short DUT. And we see that rise and fall times are reduced. The total jitter is nearly the same for the same data rate. And the symmetrical 2x through shows ringing and an implausible decrease in rise and fall times. If you look at that, that's really, let's say, unrealistically improved. The next section, we're using advanced jitter, which will solve the discrepancy, because typically a theory tells you if you reduce rise and fall times, the jitter will be reduced, but in this case, the total jitter is still very stable here. So let's have a look at that, why this is happening. We're going to the advanced jitter analysis and look at the components it will display. The advanced jitter option allows several analysis options. As you can see here, there are about 10 that we turn on. We have also some comments why we do that. I don't go through all the details here, but important particularly is the spectrum, to see that RJ plus OB spectrum is uniform. This gives you a good idea whether the separation works well for you. And the focus here particularly is on the DDJ, on the data-dependent jitter, as the most noticeable effect will be here. And the other parameters I use just to make sure that we have a correct separation of the jitter. The results for the jitter analysis, you see a screenshot of the no Deembedding on the 5G signal. We did the advanced jitter analysis for all the models. So not only the 5 models, we added also the no Deembedding as well as the open short DUT causal model. And we did that for all the data rates, the 5 and the 10 gigabit. We see that we have a good coincidence between the measured rise and fall times on the waveform, and particularly also with the estimated step response, which you can see here in the lower part. And the total jitter matches with the previous eye pattern measurement per model and per data rate. And we also can see on the next slide, where we have all the data available, that the total jitter is dominated by the DDJ. Just that the symmetrical 2x through, encircled in red in the next page, shows a large overshoot in the step response and an unrealistic DDJ. So here's the total data. We grouped that in terms of model and data rate. A lot of data, but not so important. As you can see, the TJ is nearly constant here, but you see the overshoot for the symmetrical 2x through is very large and, in my opinion, unrealistic. And also strange behavior is that the DDJ for 5 gigabit is reduced, but the DDJ for 10 gigabit is increased. So this is a not consistent behavior. And this points you to the idea that this doesn't give you a good model here. Before we go now to the next slide, which is the summary for the oscilloscope, I would like to have a closer look into the practical measurement with the oscilloscope and guide you through a measurement there with the oscilloscope. So starting here with the two channel setup, channel 1 and channel 3, we couple both together to make that easier to handle. We set up the correct scale to 65 millivolts per division, and then we basically need to do manually the D-skew of channel 3. I measured that before, it's around 9 picoseconds. This is very important because otherwise you will see a larger common mode signal. Once we have done that, we can go to the vertical menu and basically turn on the differential mode. Switch here from channel 2 to channel 3 and then turn it on. And now you see that the differential signal as well as the common mode signal appears. A nice feature is that the common mode signal is still active in the iconized display in the bottom. Now we set up the database here, the time base, changing it to the 200 microseconds acquisition time, as we discussed before. Now, in order to run the eye pattern analysis, we also need to change. First we turn on the measurement of rise and fall time for the differential channel. So rise and fall times as well as the peak to peak is analyzed. Peak to peak just for safety that we don't have an overrange. But we want to analyze all the rise and fall times. That means we have to increase the number of events per acquisition. And very important also, we have to check the reference levels because by default we have 1090%. So here we do a manual adjustment, but put the reference levels to 2080 as it is defined. And then we can manually adjust that easily, and we have a good grip on the correct rise and fall time measurements. Once we have done that, we now want to have a look at the eye. In order to display the eye pattern for such a waveform correctly, we have to turn on the correct trigger. And we have to do it for sure on the differential channel. So we go to the hardware CDR, set it to, or set the trigger first to the correct channel, and set the hardware CDR to 4.98 gigabits per second. So that's already correctly configured, and the relative bandwidth is 500 as it's defined in the standard. Now we can change the display, turn on infinite persistent for the eye pattern, and also increase the slices per acquisition so we see all the eyes or the bits patterns from the complete acquisition in the eye pattern. Yeah, I have to turn it on, sorry. Now the eye pattern appears. It looks very nice. So for the measurement, we have one measurement group where we measured on the live signal, and then we measure the eye pattern as a measurement group 2, and then we're going to the histogram measurement. Now we're changing the vertical scale, because if you turn on the Deembedding, what I'm going to do now, it will turn out that the scale would be too small. Now we turn that on, we load the correct Deembedding file. In this case, we use the symmetrical 2x from the VNA that we did before. Very important is to check whether the port order is correct. You can see that, for example, with the S21, it should start at 0, at frequency 0. Once that is correctly configured, I can enable the embedding. And once I have that enabled, I can check the response. The magnitude should look flat. There should be no ringing in the step response, and the group delay should be not excessively negative. Having done that, here you see already now the symmetrical 2x issue that we had before was the overshoot and also the unrealistic rise and fall time. So this is an example how the Deembedding works and how you can detect the issues in the eye pattern. So let's go back to our summary here. Going to the oscilloscope summary, the Deembedding shifts the reference plane from the coaxial connector of the test fixture to the USB connector. The associated attenuation of the fixture PCB is removed consequently. Eye patterns opens up and rise and fall times are reduced due to less attenuation. The total jitter is not reduced as the DDJ will be in the same range. That has to do that you move the reference closer to the transmitter. Pre-shoot and de-emphasis will cause a similar DDJ. Incorrectly developed models show artificial ringing and increased overshoot, implausible values for rise and fall times. The symmetrical 2x is an example for this. Now, looking at the good models, so correctly models show consistent measurements, plausible values for rise and fall times, a smooth DDJ histogram, do not differ much whether the model is generated with a short or not, causal or non-causal. And this applies to all 4 models, by the way, the open DOT, the open short DOT, the open 2x and the open short 2x through. So having said that, It's now a choice of you what you really need to do your measurement and your characterization. And with that, I hand over to Martin.
Matthias, thank you very much. I think we have seen a lot of comparisons doing models with different combinations of de-embedding coupons and test fixtures. I think that was very insightful. There's more material available. You see here, there's a general application note about accurate test fixture characterization and de-embedding. There's another application note coming up regarding the topic that we have discussed today, providing even more details about this background. And there are further materials available as you can see here. With this, I would like to say thank you for your attention. Thank you for watching this webinar and see you next time. Bye-bye.